Okay, well, welcome everyone to this very special event on life, the universe, and everything, the next 50 years of astronomy. This promises to be a fascinating excursion into what we can hope to discover over the next 50 years, which, by the very nature of the subject, we can glean simply by looking up. The focus on 50 years comes about because this event forms part of the celebrations going on at the University of Cambridge to mark 50 years since the inception of the Institute of Astronomy, or the IOA for short. And indeed there's a major international conference going on this week at the IOA, and many of the delegates are probably here in the audience, eager to find out what we're going to learn in the next 50 years, as am I. So for those of you who haven't found the IOA, we're down Madingley Road. You might recognize there's a rather impressive observatory building there, which was built 200 years ago, and so astronomy has been going on the site for over 200 years, even though the IOA is only 50 years. And there's a talk on tomorrow evening at the IOA on the history by a couple of our audience members. If you hopefully some of you will be coming along to that. So I should introduce myself. I'm Mark White. I'm one of the co-directors of the IOA, and my other co-director is Kathy Clark, who's sitting here as well. And the members of the panel that we have here today to tell us about the next 50 years are also faculty members at the Institute. We have Professor Niku Madhusudan, or Madhu, whose research is into extrasolar planets, so planets around other stars. So he'll be covering the life aspect. Then we have Professor Hiranya Pires, who's a cosmologist who studies the nature of dark matter and dark energy. So she'll be covering the universe aspect, which means that Professor Vasily Belukharov must be covering everything. I don't think Vasily would describe his research as covering everything, but he covers structure of galaxies, which in astronomical terms sits intermediate in scale between what we consider to be very small planets and what is very big, the universe. And so between them, they do cover everything. And to guide us through the discussion, we have Dr. Matt Bothwell, who is the public astronomer at the IOA. And so he's responsible for all of our fantastic array of outreach events, including the public, open days and the public observing, which we have every Wednesday over the winter from October to March. So unfortunately not going on at the moment, but please, if you're around, you'll be very welcome to come and join us for those. So you don't need to hear any more from me. I'm as excited as you to hear about what we're going to learn in the next 50 years. So please, can you join me in giving a very warm welcome to our panelists and to Matt to lead us through this discussion.
Wonderful. Well, thank you all for coming, and thank you, Mark, for the introduction. So the format of the evening, just so you know, it's not a sort of traditional public talk. We're not going to lecture at you. We're here to discuss and talk, as you probably guessed, about life, the universe, and everything. The first half we're going to discuss amongst ourselves. I've sort of prepared some questions to sort of stretch the panelists. But then the second half is going to be up to you. So over the second course, the second half hour of the evening, we're going to hand it over to you guys to ask all of your most burning questions. So before we get on to the questions, maybe we could just learn a little bit more about what our panelists actually work on.
Hi, I'm Niku Madhusudan. You can call me Madhu. I work on, as Mark pointed out, I work on exoplanets, planets around other stars. More specifically, these days, my group works on trying to find habitable environments and signatures of life on planets around nearby stars. And we do that primarily using the James Webb Space Telescope, but also large ground-based facilities, so a combination of various facilities that we have in the world.
Cool. I'm Vasily Belukharov. I'm a data scientist, or more precisely, sky survey scientist. I look at vast data sets that cover the whole sky, containing hundreds of millions, maybe billions of objects, with many entries for each object. The focus of my research is on, as Mark said, on galactic structure and galactic dynamics, and also stellar evolution and time domain when things change on the sky. And the questions that I'm trying to answer are, how do galaxies form and evolve, and what role does dark matter play in that process? And the data that I can't take my eyes off most recently is that produced by the European Space Agency's Gaia Space Observatory. So Gaia is special because it gives you, instead of this cartoonish 2D view of other objects on the sky, it gives you a 3D view of our galaxy. And you know, the first time I went to the movies and watched Indiana Jones in 3D with my kids, that was exhilarating. I screamed my lungs out. So you can imagine that's the feeling I have every day in my office working with Gaia data. In fact, it's not 3D, it's 6D, because not only it gives you positions, it also gives you velocities of all objects on the sky. So it's pretty special.
Hi, I'm Hiranya Perez. I'm a cosmologist. That means I study the origin of the universe, how it's evolving, what it contains, and hopefully hope to learn something about its eventual fate. So these are really big questions. And so what we do in cosmology these days is that we work more as data scientists, actually. We work in very large international teams, and we observe the sky at different times in the history of the universe. So the very earliest light we can see in the universe is a baby picture. And when we observe galaxies at further and further times away from us and distances away from us, we see the universe as it was in the past. And we can piece together a story from the origin of structure all the way to the present and see whether that picture holds together. These days, we think we can't actually answer these very big questions just by looking up at the sky. So we are coordinating with our colleagues who are making laboratory experiments as well. And they are looking for example, the dark matter particle in the lab. So in my own work, I try to do a bit of all of these things. I like to make theories about the early universe. I like to test those theories with data from the sky, and also work with my colleagues in the laboratory to see whether we can identify the dark matter particle.
Wonderful. Okay, so to kick things off, so we're here to celebrate 50 years of the Institute of Astronomy. So sort of getting in our virtual time machines and going back to 1974, if you could talk to an astronomer in your field from 1974, what do you think, what discovery of the last 50 years do you think they would find most surprising? Maybe we'll start with Madhu.
Yeah, I mean, in my field, in exoplanets, we have gone through a major revolution in just the last 30 years. So 50 years ago, just imagining what it was like, it's a surreal change actually, because 50 years ago, we did not know of any single planet outside the solar system. We just knew about, if you thought about planets, that meant the solar system, and all our formation, all our theories of how planets form, evolve, all of those were fine-tuned to what we saw in the solar system. But today, we know of over 5,000 planets for sure, but we also know that the statistics is that almost every star, you go into the night sky, pick some random star, chances are it has a planet around it of some kind. So we got this demographic information now that planets are extremely common and they're extremely diverse of all kinds. So that is one thing that will really surprise if we were to time travel and tell our former colleagues at the IOA 50 years ago that this is going to be the case, they would be shocked. I want to mention one very important aspect which relates the IOA to the first discoveries of exoplanets. So the first discoveries of exoplanets were made with this thing called the Doppler technique, where you see this wobble of the star and infer the tug of the planet on the star, and hence you infer the planet from that wobble. Turns out that technique was first demonstrated at the IOA. So one of our colleagues, there was a seminal paper from 1967 when that was demonstrated, and then that was what was used. Had they realized that is the technique that's going to get us the first planets 20, 25 years later, it's revolutionary to think about it that way. Of course, they were doing it for stars. They didn't know that about 30 years after that was the technique that was used to discover. So these are the kinds of things that will both really amaze them and also make them very pleased with how the IOA has been at the center of this big revolution that's happening.
I like it. You can argue this whole field started here in Cambridge, right? It's
a lot of it, yeah.
How about you, Vasily? What was most surprising to 1974, Vasily?
Yeah, I think even before talking about discoveries and surprising discoveries, I think most astronomers, not just in Cambridge, but anywhere, 50 years ago, probably most scientists 50 years ago, would be shocked and surprised at how we do science nowadays, how astronomers do science nowadays, how we, not only we conduct our experiments, but how we share data and ideas. Right? And I think we've led the way. The community has evolved, the astronomical community has evolved to share ideas freely on archive.org every day. We've learned that we should share our data freely. Almost 90% or more of all astronomical data is publicly available. And now we even share our code, the tools we use to carry out the analysis. So this is something that I'm very proud of, but it would be shocking and inconceivable 50 years ago. So going back to 74 and the IOA and astronomers here back then, I would say dark matter that we already mentioned today would be a very new and unusual concept. Some mavericks just about pointed out that there is a mass discrepancy in some of the largest structures in the universe, galaxy clusters. And this discrepancy arises because you can compute the mass of the galaxy cluster two different ways. You can just count all the galaxies and add the amount of light you see from them together and get one estimate of the mass. And another estimate can be obtained by measuring their velocities and computing so-called dynamical mass estimate. And you should all have an intuition, I think, for why velocities translate into mass, right? If you think of astronauts, and we have one in the audience today, if you remember how some of them ended up on the moon and had a lot of fun playing around, jumping, right, and going quite far up, right? And that's because there's not as much mass there on the moon, right? So you can imagine if they had some superhuman abilities, they could jump as high as to leave the moon, right? So depending on the kick velocity, you can actually leave the moon and travel in the outer space. So you can imagine now an army of astronauts jumping around the moon, and only those with small velocities staying bound to the moon. Around the Earth, you'll actually keep all these astronauts together. So there is some connection between the velocity the body travels with and the mass of the massive thing holding it. I think I got you all confused. Yeah. So I hope you come back to me with follow-up questions.
I think it was the thought of an army of astronauts.
I like to imagine, that there's an army of astronauts with jetpacks, kind of trying to fly about. Yes. So there is a way to connect the velocity to the mass. And so those two estimates turned out to be completely discrepant. There was a gaping mismatch between two. And so it was suggested there must be some substance, unseen substance, that keeps those galaxy clusters together. And so little by little, other astronomers started to suggest that maybe dark matter or this unseen matter is useful to keep galaxies together, to keep galactic disks flat and rotating for long enough time. So going back to 1974, I would probably talk about dark matter to Donald Lindenbell, who was the first director of the Institute. And not only Donald was the first director, he was probably the most active member of the Institute until recently. At every talk, Donald would be sitting in the first rows, and after the talk finished and the clapping subsided, his hand would be the first up, and he would always ask the most intriguing, provocative, unexpected question. So Donald was also a guru of galactic dynamics, And so I would explain to him that now we see evidence for dark matter in every galaxy we can try to measure the presence of dark matter in. And surprisingly, the ratio of dark matter to ordinary matter actually varies widely across the universe. There is some universal average, but in different environments it's very different. So here in this lecture theater, this ratio of dark matter to ordinary matter is actually very low. It is just matter that we can see, us and the furniture, and not much dark matter. But in a dwarf galaxy or on the outskirts of the Milky Way, the opposite will be true. There will be plenty of dark matter and almost no ordinary matter. So that would be quite a shock.
Excellent.
I'm not a historian of science, so I'm not going to give an exposition about what people thought here in Cambridge in 1974, but thinking generally about what people knew about the universe. So 100 years ago, we learned there were other galaxies, and soon after that, we discovered the universe was expanding. So that was known. The cosmic microwave background, the very earliest light you can see in the universe, had already been detected in 1965. I believe Vera Rubin had done her seminal measurements of galaxy rotation curves already by 1970. 74 was the year of Stephen Hawking radiation papers, so people were starting to think about what happens to black holes, and that is still underpinning cosmology today, this connection between general relativity and quantum field theory, and how we need to make those things fit to explain the very, very early universe. Those steps were already being taken. But cosmology was a very, very speculative field back then. I think they had a lot of hints already about the current picture of the universe that we see today, but the data was very, very sparse. The current expansion rate of the universe, what we call the Hubble constant today, that was discrepant by a factor of 2 by different methods measuring it, and they disagreed by factors of 2, and people were having great debates about that. It was unclear to people what types of sources were within our galaxy and outside our galaxy. So the distance scale of the universe was being established in very, very, very early days. So they had all these hints, and yet there was still the steady state theory. So Fred Hoyle at Cambridge was a proponent of the steady state theory, and that was being still debated in comparison with the Big Bang model. So I would say, looking back with hindsight, having seen the cosmic microwave background, the idea of a hot Big Bang was basically established, but those debates were still taking place. So what's changed up to today is that we have a very precise picture of the origin of structure, like an instant after the Big Bang, all the way to today, and we have a coherent story about that. But 3 of the ingredients in our standard cosmological model are what I would call tooth fairies. Our best theory for the origin of cosmic structure in the form of quantum fluctuations that got stretched out to the size of the universe at very, very early times, that postulates a so-called inflaton, a quantum field that has not been detected. We see consistency with its predictions in our data, but we don't know that this fundamental field exists. Until very recently, we didn't know any such fundamental field could exist till they discovered the Higgs field. And so now we know nature can make quantum fields of that nature, but we don't know that the inflaton exists today. Dark matter, again, there's a lot of empirical evidence for dark matter. We already heard that. But we have not identified the dark matter particle yet. So again, it's a tooth fairy. It explains all our observations to date, but we can't point to a particle physics phenomenon and say this is dark matter. And I think the thing that would have really, really confused and mystified them is what we now call dark energy. The expansion of the universe is accelerating with time. And this is a behavior, without going into technicalities, that is very, very hard to explain in terms of standard theories of physics. And it postulates the existence, again, of beyond standard model physics. or the cosmological constant, which is unexplained to this day. Einstein called it his biggest blunder, but it wasn't. The universe seems to have a cosmological constant, and we still can't explain it. And that would require probably some kind of theory that encompasses both general relativity and quantum field theory and puts them together without making them contradict each other. So there are huge mysteries. We have all this data about the universe now, and everything that we have learned, we've answered age-old questions. We've answered the question of how old is the universe to percent precision, sub-percent precision. But the questions that have been opened up by looking at the data are even bigger, and we're still working on those for the next 50 years and maybe beyond.
I do find it incredible how far we've come. I remember being in school and there was a debate raging about whether the universe was 10 billion years old or 20 billion years old. Now we've had it to percent level. It's unbelievable. So yeah, okay, so I'm going to take you up on your point about looking to the next 50 years. So we're going to look in the opposite direction now. I'm going to ask you a question in two parts, really. So first of all, what question in your field do you hope will be solved, be answered by 1974? And also, if you're comfortable answering this, what question, maybe when you're having sleepless nights, do you worry might not be solved by 2074?
Yeah, so in exoplanets, we are undergoing a major revolution right now. So just in the last 30 years, as I said earlier, we went from not knowing any planet outside the solar system to today knowing that they're very common. So the frontier has now shifted to understanding what these planets are made of. So today, the state of the art is to use these major facilities to look at the atmospheres of these planets and see what the atmospheric compositions are, and see if we can say something about the surface process, the atmospheric physical and chemical process, and so on. So there's a lot going on in terms of all the things that you can learn about planets from these sorts of observations, but I think we all agree that the search for life is arguably the biggest question that we are after. So I would say, I mean, that's very much on right now. That's what we are looking for. The current facilities are at the cusp, at the the boundary of what we might be able to do in terms of the search for life. So if you ask me in 50 years, what is it that I hope will happen? Most likely, we would have discovered life around in another planet, and I say that with some enthusiasm, but also with some trepidation, because that is a question. I mean, it's a very profound reality that we are living through right now, right? I mean, for thousands of years, we as a species have been thinking about this problem on multiple levels: philosophical, scientific, societal, and so on. So the implications will also be as deep. So it's not something that one says lightly when one says, we are out there to discover life. If you're a serious scientist, you would very well know what the implications, the ramifications of that discovery would be. So I say that with a lot of caution and optimism, knowing what facilities are coming, that if there is life out there and has atmospheric signatures, then we know that given our capabilities, in the next 50 years, we ought to be able to detect it. And we ought to be able to detect not just life on one planet, but on multiple. So we could easily be talking about 10 planets or more where we could detect such signatures. And this is not 10 years ago, this would all be theoretical extrapolations, but now we actually have a facility, and there are multiple facilities that we know will be coming on a 20, 30-year time frame. So today, we're just fortunate that we can even talk about these things as a realistic possibility. So that is what I think will happen is, in my optimistic sense, we would be talking about statistics of life in the universe rather than asking the question, is there life elsewhere? And that's mind-boggling if you think about it, right? What kind of life, how many planets might be having life? Is it like microbial life or advanced civilizations? That's not science fiction anymore. That is well within the realm of what science can do on a 50-year time frame. Then
That's what happens to the exoplanet field, right?
Yeah,
We
yeah,
went from
exoplanets
finding individual planets being incredible, and now we have statistics.
yeah, and the diversity you see of these planets is astounding. Like all
Right.
kinds of planets we are seeing. And then you asked, what am I worried?
What keeps you up at night? What makes you worry that you might not be solved?
Well, like almost every night these days, so we have these data sets already coming. I give you a 50-year time scale to find life, but I also worry that we might end up detecting a biosignature on a 3 to 4 year time scale, because that is also within range, right? So we are looking at this vast open territory right now. We don't know what kind of life is out there, and in our optimistic estimates, in one scenario, we can actually detect, and we have predicted this, like even before JWST went, that if such life is out there on these special kind of planets that we look into, these Haitian worlds, these ocean worlds with hydrogen-rich atmospheres that we work on here at Cambridge, if such life exists, we ought to be able to detect it on a few-year time scale. Now think about that, right? So those are the kinds of things that keep me up at night.
What if we're too successful too quickly?
No, the ramifications of that are immense. I don't say this lightly, because you don't want to identify a molecule and ascribe it to life and realize that there are other processes that can also make it. So what you want is a robust detection of a signature, but also a robust identification of it. So if you're one pessimistic scenario is that we may be able to detect several molecules, but we may never be able to figure out that is uniquely from life. You may end up with a false positive, and that may take much longer than actually detecting the molecule, right? In other words, proving that a signature is from life may take longer than actually detecting a potential signature of life. So this is like the scientific intricacies now we are getting into. And those are the kinds of technical things that keep us up at night.
Vasily?
Well, before planets can form, or stars can form, or galaxies can form, dark matter has to clump together and provide these first seeds for the rest of the structure to appear. And that's our current understanding of how the universe comes about. And so not knowing what dark matter is very vexing. And as I said, 50 years ago, you ask astronomers in Cambridge and they would be surprised that you're so worried and concerned about dark matter, and what kind of dark matter they wouldn't even worry about. And now we know the sort of dark matter, the type of dark matter we need in our universe. We need the cold variety. This is a special variety of dark matter that doesn't move much, and that's why it clumps together so easily, forming these initial seeds for structure formation. And it so happens that many of these seeds remain unused. And we end up in the picture of the universe when in our galaxy we're surrounded by swarms of dark matter clouds flying about without any normal, ordinary matter in them. And that's what, how I lose sleep at night, imagining that. And will we ever discover these thousands of empty, dark, invisible clouds of dark matter? So we have an indication that probably this theory is true. And this comes from multiple lines of evidence, but in particular from recent discovery of a large number of small galaxy satellites around our Milky Way. And for a while, these galaxies were not observed. They were missing. Now we know that they are there. We've detected them. They are strange. They are already quite unusual. They're unusual in the sense that they have so little light in them, so few stars, but they are so large that you don't actually see them on the images of the sky. On the photograph of the sky, they are invisible. So now you can imagine if you're up after dark, you can look up at the sky and imagine there are hundreds of these ghostly dwarf galaxies with apparent size of order of a moon. So they're not small, right? So these things exist. Now can we push the frontier and find dark matter clouds, dark matter halos that are completely devoid of any light? And so that could be my next frontier that I would happily work towards.
Do Do you ever, well, one quick thing on this, do you ever worry that dark matter might be just fundamentally unobservable? Right, is there a chance that we just don't find dark matter? Like we can see evidence for it everywhere, of course.
As in, if we don't
detection
detect in laboratory.
I'm about to talk about
exactly.
that.
Okay,
there you go. There you go.
I will defer to Hiranya.
I don't want to steal Hiranya's thunder. Yes.
Okay, Hiranya, what do you hope we'll find in 50 years?
I think well before 50 years, we will have some chance, very robust chance of detecting dark matter particles. So there are two different theories that are, well motivated for reasons other than the fact that we saw something in the sky and we invented a phenomenological concept to explain it. There are mysteries in the standard model of particle physics that require an explanation. And before we started seeing dark matter in the sky, already people had hypothesized that two types of particles called WIMPs and axions. So physicists have a peculiar sense of humor. WIMPs are weakly interacting massive particles, and axions are literally named after a particle which is a type of detergent. So a detergent that can wash away the sins of the standard model. That's really why it was called an axion. So these two classes of particles are well motivated from a fundamental physics point of view because they solve problems other than explaining dark matter. So experimental attention has focused on both of these hypotheses for some time, but for sociological reasons, people have focused on the WIMP hypothesis. And essentially, how do you find a WIMP? You put a giant atom or nucleus and into a very, very large tank, and you are waiting to see whether this nucleus is impacted by unseen particles and emits some kind of energy or current that you can read out. So people are building bigger and bigger versions of these types of experiments. And in fact, the UK is bidding to host the final word on these kinds of experiments and put it underground in the Bulby mine, which is in the northeast. And this is an active thing that the UK is currently campaigning for. So we could even have this dark matter observatory here in our country. The other type of candidate, axions, my favorite dark matter candidate is the QCD axion. And there is a precise prediction for its mass, which is unlike some of the other dark matter candidates that very, very clever theorists have come up with. And finding this kind of dark matter is more like tuning a radio. There is a wave-like property to this dark matter candidate, so you have to tune into its wavelength, which is defined by its mass. So it's a completely different kind of experiment. And both of these types of experiments have really, really come on very tremendously in the last decade, especially the axion type. And very clever experimentalists are building extremely sensitive instruments to look for these. So I'll be very disappointed if we have to wait 50 years to find the dark matter candidate. So I'm quite optimistic about that one. What keeps me up at night is dark energy or the cosmological constant. I think that this observation that the universe is accelerating reveals a really, really deep conceptual issue in our theories of fundamental physics. Everything that we know about the very larger scales and the very smaller scales are described by two theories. On very larger scales, it's general relativity that describes the evolution of our universe. And at the very smallest scales is quantum field theory or quantum mechanics. And these theories are incompatible. And the fact that we don't understand why there's a cosmological constant and why it's so small reveals that there is something about fundamental physics that we really need to get to grips with. And this is such a major problem that there's very, very little theoretical attention on this. It's such a big problem, people prefer to work on something easier. And if there are young people in this room, just go and grab the hardest problems and wrestle with them. Because then you will perhaps do something that doesn't keep me up at night. I'm not clever enough to solve this problem, otherwise I would be working on it. But this is the thing that keeps me up at night. And I have one more thing for you. Our best understanding of the beginning of the universe leads us to believe that there is a multiverse, that there are other universes outside our own. This is not science fiction. This is an implication of our best theories currently. So when your theory points to an extrapolation like that, you have to take it seriously. And yet, we might never have a way to observationally or experimentally test this implication. And that also keeps me up at night.
I guess it's like inside a black hole, right? You might never be able to actually see.
Indeed.
But we just have to trust the theory in some sense.
Yes.
Okay, so that's plenty to keep us up at night. We're just over the halfway point, so I might turn it over to you guys and have you do your worst. So there's a couple of runners with microphones. So you can ask a question to the whole panel if you have a particular question about fields of planets, galaxies, the universe, you can direct it to the relevant person. So if you put your hand up, someone will find you with a microphone.
Hi, good evening, Matt. Good evening, panelists. Thank you for your illuminating comments. It's generated a whole host of questions in my mind. I've got a couple I'd love to ask. There's two I'd like to ask, but I'll ask one. If there's time, we can come back to the other one. We saw lots of hype in the news about how the recent JWST results had broken the Big Bang, which we know is relatively nonsense. But it has shown that there are galaxies that are more luminous than we expect to see at that stage a few 100 million years after the Big Bang. This could be explained by stellar starburst type activity or an overactive galactic nucleus or something. But that leads to a second problem, which is how do we get such a large black hole so early in the universe? The second problem is seeing structure in these galaxies that we don't expect to see in such young galaxies. So this is really to Hiranya and to Vasily, so sorry, Madhu.
No, that's fine.
What are your thoughts on what you would require changes to the Big Bang model, or rather, more specifically, the lambda CDM model, to fit in and explain what the JWST is showing us with these large number of galaxies?
It's possible we have different perspectives,
Yeah,
so why don't you start?
Okay. Yeah, from maybe galactic perspective, a life of a galaxy. So first thing to point out is these observations are extreme, right? And these observations are new, and they just announced to us earlier this year, right? And these photons come to us from the period in the life of the universe that is not so far from Big Bang, right? 300 million years or so. So the one thing to remember is, of course, that when any telescope looks at objects that distant, the light from the distant galaxy is redshifted, so it's stretched, and it becomes redder compared to the wavelengths at which it was emitted, right? So when JWST sees galaxies in the early universe, JWST observes the universe in infrared. But the light it actually sees was emitted at these very early times in the life of the universe in the ultraviolet, right? And so this ultraviolet light is not contributed by anything in the galaxy. It's contributed by the hottest, the youngest, most massive stars in that galaxy and hot bubbles of gas around them. So these are the stars that don't live that long, right? So the lifetime of a star is inversely proportional to its mass. So they live maybe 1 million years. So we have a very short glimpse of the life of a galaxy, of the processes of conversion of gas into stars. And from this, we start to interpret how massive these objects are. This requires an assumption of how steadily it's making stars. But we can't really make a measurement of that because we only see the youngest short-lived stars. I have a very beautiful metaphor to explain how silly that is, but after my previous metaphor, I'm not sure if I should give. But you should ask me afterwards. You will be impressed. So I think so bursty star formation history in a galaxy, our extrapolating outside of the UV range into the rest of the spectrum of the galaxy may be an oversimplification. And in fact, we know that galaxies in the early universe live very tumultuous lives, right? They have bouts of activity, and then they have bouts of lull, of inactivity when they rest before the next burst. And so if we observe one during the burst, we would conclude that they're overluminous. If we observe one during the lull, if we detect it, we'll say it's underluminous. But I think it's too early to claim a discrepancy with our theory of structure formation. And the discrepancy comes from the fact that if there are already luminous galaxies that assembled a lot of stellar mass, it means that they live in massive dark matter halos, because, as I said, all galaxies live in dark matter halos, but there was not enough time to put these dark matter halos together. So that hence the problem with our theory of structure formation. But it may be explained simply by a very bursty, tumultuous life of early galaxy.
I think actually our perspective on that is very similar, but let me just make a general point about the way that cosmology is going as a field. It used to be the case that you could study different epochs in the history of the universe and get data, and the data was quite clean and you could interpret it mostly by physical modeling. But these days, our understanding of cosmology is really tied to the life and death of galaxies. And the earlier we observe galaxies, the less our understanding of the co-evolution of the dark matter and the galaxy. I also think that if some of the observations you're talking about came from just taking pictures, right? We have to then wait also for the spectra, because the spectra actually have much more information that can help discriminate between, is it a starburst galaxy at high redshift or actually a very close by galaxy that we have misinterpreted. It's not at high redshift, it's actually at low redshift, but it's red. So these kinds of mistakes can happen if you don't have spectra in addition to images, and that could also be going on. You also mentioned black holes. So there, I do think that the models are challenged because it is increasingly quite difficult to work out why such supermassive black holes were forming so early in the history of the universe. And this could be tied to a question about what are the seeds from which such black holes originate? And this is an open question. So to summarize, basically, we have to have, in the end, a theory of the co-evolution of the dark matter, the galaxies, and their black holes. And then we can say we understand structure formation. Currently, we have pieces of this puzzle, but we haven't put it together yet.
I understand that some of the redshifts have been corrected at a much level than we actually thought they might be.
Indeed.
But that leads on to one other question.
Do you mind if we move on, actually? Because we don't have all the time in the world. We want to give everyone a chance to weigh in if possible. There's a question there, if you can reach her, Annabelle.
Hi, lovely talk, fantastic, really interesting. I was wondering, this is probably for maybe Vasily and Hiranya. I know you're looking at the expansion of the universe, but are you also looking at the inevitable maybe destruction? Because I know that there's talk that we're eventually falling into a black hole or something, but is that also possibly understanding what could happen?
Shall I take this one? Thanks for asking that. It basically allows any cosmologist to speculate, and if we make a prediction for what's going to happen in 1 trillion years, we are not around to see whether that is going on. But, okay, so what is our current best understanding of the fate of the universe? Sadly, it's a really, really sad one. Okay, so I mentioned the cosmological constant, or dark energy. This is making the expansion of the universe accelerate. So a very long time from now, all the stars in the universe will have died out. There will be a sea of radiation and black holes. And eventually, by Hawking radiation, the black holes will evaporate. And the universe will continue to accelerate in its expansion. That means more and more volume being made. And it will become completely like a thin, very cold sea of radiation, and that is our best current guess. So combining this sad picture with my optimism and the multiverse theory, it could be that there's a lower cosmological constant to jump through, and we will open up a new universe inside ours. So that is my speculation. This is more like science fiction than science fact.
It's a lot more fun than just darkness forever, right?
Yes.
How about we stay around the same area, if that's okay? Make life easier for our microphone runner.
I was wondering if you could tell me a little bit more about the empirical and theoretical underpinnings for the multiverse theory.
Okay, so I mentioned inflation. I don't want to get technical about it, but basically inflation postulates that all of space is covered by a scalar field, and it's a quantum field, so there are small fluctuations in it, okay? So the multiverse idea in this context, there are other types of multiverses, but in this context, it basically comes from, essentially, it's very difficult to stop inflation everywhere in all of space. It only stops locally. That means it's going on in other places well outside our observable horizon. And it's only in local pockets that it ends. And only when inflation ends can structure formation begin. We need to convert the energy in this field into the particles and fields of the standard model. This is a process called reheating. This only happens once it's stopped expanding at this super accelerated rate. So the idea that this is the explanation for our local formation of structure then allows you to immediately appreciate that it can't stop everywhere all at once. So there could be other pocket universes out there. And some people even speculate they have different laws of physics than ours, but that's not a requirement. It's just that, okay, so here's an analogy which I hope works. Okay, so imagine that you are in a vast landscape of mountains and lakes and so on, right? If you're at the top of a mountain, you are in a place with high potential energy, right? That's like inflating space, because that's like having high vacuum energy. And if you drop down to the bottom of the mountain, then you have stopped inflating because you come to a place of low potential energy, in this case, low vacuum energy. But in this landscape, there are mountains and there are valleys. So if you're in a valley, you might be in a pocket universe where it stopped inflating, but the parts of space that are on top of the mountains are still inflating. So this implication is hard to escape from once you buy the idea of the inflaton. I hope that helped answer.
This one.
Let's go to this side first, and then we'll sweep back.
Thank you, the panelists, for this great talk. As an outsider in astronomy, would like to understand, what we can reach in the next 50 years. In my understanding, all the stars, the galaxies, they're million years away, in light. Do you think in the next 50 years we will find a way to reach out quicker, to beat the speed of light, or be able to go further? Because even if we find some life million light years away, we're never going to reach them out in the next 50 years. Or do you think we'll have a different way to beat the speed of light? And
who wants to take faster than light
I
travel?
think Madhu.
So the closest stars are a few light years away, and there is a chance that in the next 50 years we might detect signs of life in stars that are a few tenths of light years away. But that's all we can do. We could just infer life in those in the atmospheres, presence of life on those planets through their atmospheric signatures. But no amount of technology will be able to get us anywhere close. In terms of physically being at those planets, it's not going to happen. That said, there are ambitious plans to send probes to our nearest neighbor, Alpha Centauri, but even that we are talking about maybe 100 years, 100-year time scales, and that too sending sails, not actually people, but sending maybe robots or maybe small sails. But going there physically or sending an instrument physically is going to be a challenge for the foreseeable future. But even just knowing that there is life out there is going to be a revolutionary development.
Can I give a science fiction answer?
Oh, you can, yeah. I was just going to talk about how big.
Okay, very briefly. So there is a concept in theoretical physics called the wormhole, an Einstein-Rosen bridge, which can connect two very different parts of space through a higher dimension. So the standard reason for expecting that this will never work in practice is because the bridge, the wormhole, will collapse almost as soon as it's actually formed. But this idea that we might have a scalar field, which is manifesting in terms of dark energy, that has the kind of properties that might hold this kind of bridge open. So if we are ever able to manipulate dark energy, which might be well beyond 50 years, we might be able to make wormholes that are stable.
I'm excited about this. Great. Okay, there's a gentleman at the front who's been very patient from the start.
Thank you. My question in principle is for Madhu, but I'd like to hear them all. Which one would be the impact in human culture, human society, and human history to find out that we are not alone?
Yeah, so this is something that we think about a lot. It's an overloaded question because our best bet in the short term is to find, let's say, evidence for microbial life on these planets through some atmospheric signature. And for the so if you're really paying attention to this problem and thinking of, what it means to find life, from a scientific point of view, it would revolutionize your thinking. It will revolutionize all our thinking. Why? Because we have checked the laws of physics, whether they apply elsewhere in the universe. So on stars, galaxies, large scales, as we have heard. And as far as we know, most of them do check out, right? So laws of physics. We have also checked laws of chemistry. So atomic chemistry, molecular chemistry works, is universal as far as we know. What we don't know so far is if biology is universal. So the moment you detect any kind of life, microbial or whatever, right, any kind of life, that is your first indication that biology is universal, is potentially universal. And that is huge if you think about it. Now, fortunately, so if you go back in history, there has always been a pushback against the idea of extraterrestrial life from many quarters. Some part of society would want to believe that we are unique. Fortunately for us, for that kind of mindset, if you detected microbial life, they won't be as offended. So we are saved in that sense. So from a scientific point of view, we would have made an enormous discovery, but by the point the other mindset realizes that it's an enormous discovery, society would have already taken it for granted. So that's good. The challenge is if we discover actually a techno-signature, like actually a signature of an alien civilization, that I think would have a much more direct and immediate effect, because there are people in the world who think aliens are amongst us. There are, and visiting us all the time. So there is that. There are segments of the world which think that we are unique as humans. Even on Earth, we are unique as a species, and we ought to be unique in the universe as well. And for them, it will be a big hit to the system. So this is why I said the question is very deep and loaded, because depends what kind of life you find has a different type of implication on society. But the baseline for me is that whatever life you find is going to be a big scientific revolution in our understanding. Eventually, society, be it in 10 years, 20 years, 50 years, 100 years, will look back at that moment and realize that that's what has changed our identity forever. Because for once, we would know that actually we are not unique. Whatever form of life it's out there, we are not unique. Because once you start life, there are many ways it can go, and there are millions and billions of systems that are out there, stars that are out there, and we think there are trillions of planets across all these stars and so on. So once you find that biology is universal, then getting to intelligent life is actually not that difficult, given the statistics. But that initial point is the challenge. I hope I answered your question.
Excellent. Now, there's someone right at the back, if you don't mind the stairs.
Are there any calculations of when the universe is going to end?
I didn't hear that.
Are there any calculations for when the universe is going to end?
Okay, please don't worry about this answer, but trillions and trillions of years from now is that heat death that I was talking about. I think we should more worry about what's happening with climate change and things like that.
Yeah, I guess it goes back to the question, the previous question is the thought of reaching another civilization when we haven't actually worked out an ethical system of ours should give us the shivers.
Yes.
And so we should rush and get ourselves in order.
I agree.
Excellent. The fan's quite loud in the microphone, I think.
Mm-hmm.
Sorry. How are we doing?
Apologies.
How about the person in the salmon shirt?
Thank you. Wonderful comments, by the way. My question's for Madhu, mainly. You described the early evolution of the exoplanet instruments, the spectrometers, the Doppler spectrometers. And in the next few years, we're going to see instruments of quite unimaginable sensitivity coming along. I've got Elon Musk's credit card here, and I'm going to give it to you. What would you like to build over the next 20 years or so in order to detect life on other planets? What instrument?
Yeah, so very good question. So currently, there are several candidates for where we might detect life, both in the solar system and beyond. In the solar system, there are obviously neighboring planets. There is Mars, there is Venus, and then there are the icy moons in the solar system. These are moons of giant planets where we think there could be subsurface life beneath the icy surface. But then there are exoplanets, which is what I focus on. And the answer depends on who you ask, but I would bet on the exoplanets because there are just so many of them. And then I would do two things if I have infinite money, which is first, maybe buy out JWST because the cosmologists tend to use it a lot. So I would just buy it out and focus entirely on searching for life. And I think we would have a very good shot already with JWST, or build another JWST, which is only $10 billion. So no problem. And put it dedicated to exoplanets. That's one thing. The other thing is, which people have proposed, and it's in the works, the idea, which is to build a direct imaging telescope in the optical UV wavelengths to look for reflected light from habitable planets around nearby stars. We are talking about, again, tens of light years. Basically, the idea is we know like most of the stars that we can observe like within the few tens of light years. And we think our statistics say that almost every one of them should have planets of some kind. And we could do surveys to establish which of these planets could be in the habitable zones. And you just point at all of those planets. If you have order 25, 30 planets, you can point at all of them and get spectra. And we could get lucky and detect biosignatures in their atmosphere. So that actually has a very good chance of success. So that's another $10 billion for you. So between those two things, I think we are covered.
I mean, I'm not sure we've touched 10% of Elon Musk's wealth, right? So we
there's
plenty left over.
Exactly.
I think we're almost out of time. I think it's maybe time for one more question, I think. How to choose. Gentleman here at this front. Sorry to everyone else.
I've always, I shouldn't have missed this, but I've always found inflation a bit inelegant, and dark energy seems even worse. Is there any chance that in the next 50 years we might make a discovery that shows that either of those two is not the way things are?
That's a really good question, and I think that many people would agree that these observations and phenomenological models are inelegant, and if we could have dropped them and the observation showed us something else, then that would have been great. But the thing is, especially for the case of inflation, there were many, many theories of structure formation. And the predictions of those theories was compared with the data, and they fell by the wayside. So I think that inflation for me is a toy model. It is an idea that we see something working in practice, but we haven't understood the principles of it yet. And I think that this is an area in which theoretical progress can be made. Regarding dark energy, I think I told you about that's what keeps me up at night. There's no good explanation for dark energy that's grounded in our understanding of physics. And I maybe invite, again, people in this room, young people, to work on this really challenging problem.
Well, we started a bit late. Should we do one more, maybe?
Yeah.
What do you think? I think there's a gentleman.
This lady has been waiting for a long time.
Oh, okay. Where sorry, Hiranya?
This lady has been waiting for a long time.
Okay.
Yeah.
Something a bit different. To me, one of the most exciting things that's happened over recent years is the detection of gravitational waves. Now, I know it's not the special subject of any of you, but it hasn't had an airing at all tonight, and I wondered where you thought it fitted in this kind of spectrum of important things that's happened over the last 50 years.
I actually work on gravitational waves, so I'm happy to answer this one. You know, it's a new window onto the universe. Before that detection, before 2014, all of the observations that we've made about the sky have come from a single messenger light, right? And gravitational waves is essentially like hearing the universe in addition. And it is going to open up new horizons for us. So we didn't talk about the next generation of gravitational wave observatories, but the third generation detectors will see all the way out to redshift of 100, where we have not detected any photons from. We have no idea what's out there. Maybe it's a sea of primordial black holes, and we will see them. And so, you know, this new frontier, it's gone from the first detection to essentially a data-driven field, you know, in less than 10 years. It's even faster than exoplanets. It's a really rising field, and we still, I don't think, have appreciated how to integrate the understanding that we will get from that field into our picture of life, universe, and everything. And I don't know if you've heard, but there's yet another type of gravitational wave detection that came just earlier this year. Pulsar timing arrays detected a rolling sea of gravitational waves, which are attributed to, for example, the mergers of supermassive black holes, the stuff that I said we don't understand how they originated. You know, so we have to put all of this new data and these observations into our understanding of the cosmos, and that work is only just beginning. But great question.
Wonderful. Well, I think we are over time, unfortunately. So I think you'll agree with our panelists have done a very good job from taking us from biosignatures to dark matter to the inflating multiverse. We've answered life, the universe, and everything. Can you join me in thanking our panelists again?
Thank you, everyone.
Thank you.
Thanks to Matt as well.
Thank you, Matt.
Thank you, Matt.